Hi, everyone. My name is Justin Kottinger, and I'm a graduate researcher at the University of Colorado Boulder. This is a shared work with Dr. Almagor from Technion in Israel and Dr. Lahijanian, who is also at the University of Colorado Boulder. As the title suggests, we present a framework for enabling multi-robot motion planners to explain their solutions to a human user. Namely, I will present a meta algorithm that we call MAPS-X. Let's consider the following scenario. We have a collection of agents, each with their respective start locations and goal regions. For example, the blue helicopter wants to reach the blue target. And within the shared workspace, I have a collection of obstacles which I would like all agents to avoid at all times. As everyone here knows, this is a classic multi-robot motion planning problem, which I can easily provide to an MMP planner and possibly get a plan that looks like this. Now let's consider a different problem where a human must validate that this plan is collision-free prior to execution on a real system. We could show a video, but this is difficult to validate safety because it is too difficult to focus on all the moving agents at once. Another way to do this is to show a collection of disjoint trajectory segments. This method is motivated by psychological theories that state recognition of non-intersecting lines happens very early within the cognitive process. As you can see, the first trajectory segment is collision-free because none of the lines intersect, as goes for subsequent trajectory segments. So essentially, this is the new solution. Rather than providing only a motion plan, we also provide a decomposition of the trajectories into a collection of images of disjoint segments that are to be presented to the human user. We call these images explanations. But this begs the question, why do we even care about explanations? Well, within safety critical situations, there is little to no trust in provably correct algorithms. Rather, trained humans are used. And this can easily be seen in the realm of air traffic control, where we use human air traffic controllers rather than MMP algorithms. Explanations allow us to solve this problem more efficiently. Specifically, we could use algorithms to compute motion plans, explain the correctness of the plan to a human expert, and then allow a trained human to make the final decision to execute the plan. The goal of our research is to bring this ideal scenario to life by enabling MMP algorithms to explain their solutions to human supervisors. In order to reach this goal, we must first incorporate explanations into the classic MMP problem. To go about this more formally, we have K agents in a shared two-dimensional workspace. Each agent is described by a dynamical function f, an initial state, and a goal set. This would be enough to solve the classic MMP problem. However, the explainable MMP problem requires an explanation bound R, which is the maximum allowable number of images required to explain the plan. Thus, our problem consists of two parts. The first part is our classic MMP problem of finding safe trajectories for all agents. The second part, which is new, is that the plan can be decomposed into a maximum of R segments when projected onto the 2D workspace. This work focuses on finding a solution to the explainable MMP problem using centralized tree-based MMP algorithms. We focus on this type of planner for two reasons. First, these algorithms contain the information of all the agents within their states. Secondly, these algorithms are very well understood, which allows us to reason over the different algorithmic behaviors that explanations introduce. Let's take a look at how centralized tree-based MMP planners work. These planners begin by composing all agents into a single state and input vector. Then, by a series of sampling and propagation techniques, we grow a dynamically feasible motion tree until we find a solution. Once a solution is found, we often project that solution onto a 2D workspace to visualize each agent's trajectory. So the first part of solving our problem is to add the ability to segment the MMP solutions into disjoint parts. This can be done via a very simple algorithm. We begin at each agent's initial state and check for intersection. If no intersection exists, then we increment the trajectory by one time step. This process repeats until an intersection is found within the two-dimensional workspace. At that point, each trajectory segment until the most recent check is correlated into the same segment. Then we reset the segments and the process repeats until all agents are at their goal. The output of this algorithm is a successfully segmented trajectory. This algorithm has a few advantages. For example, we're able to segment any MMP solution from any MMP planner. Also, this algorithm provides a minimal disjoint segmentation, and we have a lemma in the paper to prove that. And also, it's quadratic in running time with respect to the number of delta t segments. However, one huge disadvantage is that we cannot change the MMP solution to decrease the amount of segments. So for example, in the solution to your right, if the number of allowable segments R is 3, this solution would be unsatisfiable, and there's no way to change that without entering the planning loop again. So our solution is to bring minimum disjoint segmentation into the planning loop. The most intuitive way to do this is proposed in an algorithm we call lazy maps X, where maps stands for multi-agent plan segmenting, and X is a placeholder variable that can be replaced with any centralized sampling-based tree planner. We will begin in the composed state space with an initial state, X0, and a goal region. And like any other tree-based centralized MMP planner, we will repeatedly sample and propagate to grow our motion tree. This process repeats until we create a node in the goal region. After that, we run our minimal disjoint segmentation algorithm to explain the plan. If this plan can be explained in a satisfiable number of segments, then we can output the solution. Otherwise, we prune the unsatisfiable portions of the plan by removing nodes that are above the explanation bound. Lazy Maps X brings on a number of advantages that weren't apparent in the first algorithm. First and foremost, bringing explanations into the planning loop allows us to tune the amount of explanations required to explain the plan prior to exiting the loop. Also, we provide the minimal disjoint segmentation since Lazy Maps X grows upon the first algorithm that we presented. Additionally, there's no need for post-processing, and Lazy Maps X maintains the completeness properties of X. However, there are still some major disadvantages to this algorithm. First, segmentations are only generated after a possible solution is found. This is a very minimal way of reasoning over the explanations while planning, and is also why we call it a lazy method. Secondly, due to the laziness of the algorithm, it does not take advantages of additive segments, which could help us find favorable motion plans when explanation bounds are strict. Therefore, we also proposed a more extensive algorithm called MAPS-X. Just as before, MAPS-X begins in the composed space with an initial state and the goal region. It then samples and propagates the dynamics one step forward. After doing so, we run our minimal disjoint segmentation algorithm on the current segment. If the node can be explained in a maximum number of R segments, then it's added to the tree. This process repeats until we generate a node in the goal region, and once there, naturally we output the solution. Due to the fact that the algorithm checked for intersections in the workspace at every time step, we are guaranteed that the solution will be explained in a satisfiable number of segments. I would like to take the rest of my time today to talk about some results. Our paper has an extensive results section, and I encourage the viewers to go to the paper for the full analysis, evaluations, and benchmarks. I will only discuss a few results here. To begin, let's consider a very simple problem where two agents are trying to go from their start locations, the smaller dots, to their goal regions, the larger circles. Simply planning with RRT, we are presented with a solution that can be hard to verify due to the fact that the trajectories intersect. If we instead plan using MAPS-X with RRT without limiting our explanation bound, we could get the same plan with the added benefit of knowing exactly where the segmentations are. Notice that this solution is much easier to verify. Additionally, by bounding our explanations to one segment, we can change the system's behavior to better accommodate simpler explanations. I have summarized the results of this case study here. Notice that in over 200 runs, both Lazy Maps X and Maps X found solutions to 100% of the problems when we do not bound the explanations. However, when we bound the explanations to one segment, Maps X found the solutions to about 90% of the problems, while Lazy Maps X only found solutions to about 7%. This dramatic difference stems from the fact that Lazy Maps X does not account for segmentations until a possible solution is found. This means that Maps X is better suited for the plans in which natural body behavior must be changed due to a limit in the bound. The next case study shows a congested space in which both agents need to navigate a narrow corridor. Notice that in this solution, setting an explanation bound to 3 allows both agents to navigate the corridor simultaneously. However, setting the bound to 2 requires that one agent waits for the other to navigate the corridor first, and then when clear, the second agent then follows. This behavior is clear when visualizing the plan using our explanation scheme. As expected, Maps X successfully found a solution to 80% of the problems, while lazy Maps X did not find a single solution. Our final case study shows how our approach can be applied to a higher number of agents. This is done intuitively since we are using a centralized algorithm. The unbounded solution can be explained in 4 segments. Notice that when bounding the solution to 3 segments, we receive a much smoother plan that can be quicker to validate. Once again, I want to mention that there are many more case studies in the paper to show different aspects of our approach. I encourage those who are interested to take a look at it. At the high level, we present a framework to transform any tree-based centralized MMP algorithm into an explainable MMP planner. We propose for MMP algorithms to explain their solutions using a collection of disjoint images that clearly show each agent arriving safely to its goal. And we present meta-algorithms to turn MMP planners into explainable MMP planners. This work actually only focuses on projections into a 2D workspace. Future work in this domain can proceed in several directions. One future direction could be to extend this explanation scheme to decentralized MMP planners, while another interesting direction would be to examine explanations in 3D workspaces. We are thinking about both of these problems now. Thank you all so much for listening, and please feel free to contact me if you have any questions.